Hello, my name is Barend Mons of Leiden University Medical Center and one of the directors of GoFair. Thank you very much for taking the time to listen to this talk on FAIR in times of crisis. First of all, I would like to talk briefly about GoFair and implementation networks, and the specific one that we see here, the Virus Outbreak Data Network, VODAN. And then I would like to focus on how we have used FAIR data in the times of this crisis. So first a little bit about GoFair. As we heard, it is an initiative of Germany, the Netherlands and France, and we have implementation networks that are groups of like-minded people that come together to do what they were already doing or do something new. They usually have their own funding, and they all adhere to the FAIR guiding principles, and they form a network. And the offices that we have support and coordinate these networks. So the VODAN outbreak, the Virus Outbreak Data Network, VODAN, is one of those INs. And its goal is to provide FAIR data points all over the world where we can go and access data about the epidemic, because as we will see, that is not something that is very easy or something that is obvious. So we are 3 directors in France, the Netherlands and Germany, the German director Klaus Tochtermann, and we have very much realized that GoFair, when it was founded by the governments in 2017, was a temporary initiative by nature. So the idea has always been that as soon as the European Open Science Cloud is up and running, we hope that some functionalities of GoFair, including maybe the successful IN concept, will go on in the EOSC, but that's not in our hands necessarily. But meanwhile, we grew very fast and we have a lot of implementation networks. VODAN is one of them, and it's there to stay, we hope, because it's called VODAN, not CODAN like in COVID, because next time we have a virus outbreak, we should be much better prepared than this time. I hope to make you understand why. So if you want to read more on the VODAN IN, there was an article published recently. You can get it, and it's open access. You can read more details about it. I don't want to spend too much time on the details. What I would like to do next is to give you one slide. Forget about reading this all, but it will all be provided. First of all, the difference between the FAIR guiding principles that were published in 2016 and the implementation choices that we have made is important, because people can implement the FAIR guiding principles in different ways. So this is one way that GoFair has chosen to implement them. And that is basically around this core propeller, as we used to call it, because we realize that you have applications like algorithms and other things that operate on data, and you need underlying infrastructure to run those algorithms and on the data. But increasingly these are distributed all over the world. And the idea that we can bring everything, sometimes petabytes, together for any particular question that we want to ask is very old-fashioned. So we need to facilitate human-to-machine collaboration, machine to human and machine to machine. That's the first tick box. In our case, we say it has to be based on FAIR guiding principles, and we have chosen an architecture according to the FAIR implementation profile and the FAIR implementation frameworks that have been described in several publications, so that all elements are machine actionable where possible, and we will work as open as possible but as closed as necessary, because we all know that not all data can be open, especially when it's sensitive patient data. And therefore we have to work as distributed as possible and as centralized as necessary only. So to do that, you need FAIR metadata, first of all, of applications, so the machine knows what the applications expect. The data should have FAIR metadata. Doesn't mean the data themselves or the background information is necessarily FAIR as well. Could be pictures that still have to be learned on by smart algorithms. And then you have the fair metadata even of the compute, so you know that you have enough compute to run what you want to run. And in the case of Vodon, we started with funding from the Dutch ZON-MW, from the Philips Foundation, with the partners you see on this slide. I don't want to spend too much time, but it is a mini implementation of this Internet of Fair Data and Services, highly focused on COVID-19. And of course, by now, we have enormously interesting and important information all over the world, from the viral mutations over the spreading time to all kinds of localization and geographical data, but also the symptoms that are getting more and more clear are all over the world, but not always easily accessible. So what we mean to do with Vodon is to have a globally spread set of fair data points, the green circles here. And then we have, of course, established knowledge in databases like you have at the EBI in Europe and NCBI in the United States, but also several companies have integrated data. And it's all about looking at the real world data and combining them with the data that we have already and the knowledge we have already about similar viruses, about immunology, about aberrant processes, as we will see later on. So in the first part, we already did a COVID-19 RDF fair data model that everyone can reuse. And we have fair data points in a box that can be easily installed. Effectively, they have already been installed up to places in Africa. And we will use the developing personal health train infrastructure to route the algorithms to the data rather than the other way around. So if we summarize the GoFair and the fair part, the machine knows what we mean. That's the key of fair. The end of data travel, usually I even say the end of data sharing as we know it. It's now visiting of data. And all data should be now, and it's half a joke that came from the US, federated AI ready. You get fair again. If we want AI to go to the data in the future, then the data better be AI ready to be learned on. So that sounds very logical. And then the question comes, why didn't we have this already? Or is this a dream? Actually, right now in the crisis, people are saying, fair is for the future. It's a dream. It's nice, but not for now. Let's do it the old-fashioned way. And then we see what happens. So what we did, to give you an example of our own research and the driving force to get fair data, is a pretty complicated workflow as it looks, but it is not so difficult. On the left-hand side, the A1 panel, you see that we took a lot of information from papers that came out and 3 key papers to form a particular hypothesis of what actually happens in COVID disease. And the green panel, the A2 panel, you see that we have real-world observations. For example, the case report form of WHO, on which our COVID fair model was based. We have actual measurements, as we do them now, for example, in the Leiden University Medical Center, but in many other points of care. And we have an increasing number of apps that people use on their smartphone, on self-reporting. So that we classify as real-world observations. New observations that are real and are seen. And of course the papers also contain hypotheses, so you cannot separate the left and the right hand side of this picture entirely. But the first step is that we believe that all stuff that needs to come out of this should be fair at the source. In this study that we did, we spent 90%, not 80%, on data munging rather than the analysis of the data. Because most of the data are not fair. Papers are inherently not fair, and that should change. Then on the right hand side of this picture, you see here that there is a hypothesis, in this case that the SARS-CoV-2 virus interacts with the human proteome. We know that there is 26 predicted proteins of the virus that will then have predicted interaction with maybe more than 300 proteins in the human proteome. And one of them that everybody knows by now is ACE2 and ACE. And then there is also the hypothesis that the virus would cause a cytokine storm, aberrations of the immune system, the RAS system, and cause all the troubles that we see in severe patients. But some patients only get a cytokine release syndrome and get better and control the virus. So we have put all this data together, and that resulted in the center here at D, a disease model that I will show you more about later. And now we actually have an in silico environment where people can test new drugs that they think could work for patients immediately. And of course, this is not replacing in vitro or even later on clinical testing, but it's at least what we call a rationalization of whether this drug might work. And I tell you one thing, the very limited value and the dangers of hydroxychloroquine would have come out much earlier in this model than we had to go through a much longer process before we could even rationalize why the drug would work or not. So this is just to show how we did the three major papers. We made the FAIR digital abstracts, which are now connected graphs of the concepts that are mentioned in those papers. And then we set together with the clinicians, one in particular, Dirk-Jan Kuipers, who was analyzing the pictures you see on top here, the CT scans of the thorax of the severe patients versus normal patients. And we saw in the first rows of this Excel sheet what are the typical observations that we see in patients when they go from not even being in the hospital to death. And then we already did some gene plugging in here from our in silico system, but we will go to that later. And then we see what is the underlying mechanism that we expect. That's the hypothesis. And then at what time in the disease, and we are still working on this, as you can see, we would have the best therapy for this particular patient. Because the worst we could do now is, now that we understand what's happening, you see that we are now probably going to treat every patient the same? No. If patients are in the early phases when they come into the hospital and they may be in danger to develop a cytokine storm that goes out of hand, you have a very different intervention than a person that is already way down that path and has thrombosis and vascular leakage. So when you plot our in silico model that is based on a lot of FAIR data, more than 200 databases actually around the world, on this same disease model, you see the red dots here are the diseases that we see. And if you start on the left hand side, you see that if people get a normal cytokine release syndrome, so their immune system starts working, you see that you get all the symptoms you see on the left hand side. I don't have to read them to you, they're all absolutely clear. If you move on in the disease, you get vasculitis, then you get alveolar damage and capillary leak syndrome, so your capillaries start to leak. Then you get more severe extravasation and you get thrombosis on top of that. And then of course, dependent on which organ that is most severe, you get pulmonary embolism and organized pneumonia, heart failure, stroke, septicemia and other things, actually multiple organ failure that usually leads to death. Now at the bottom of this model you see a lot of orange balls, which are genes that you would not all of them normally associate with the immune system. And a lot of this is a immune system that went astray, but there is more. And don't even try to understand this picture, it's just to show you how complicated things are, that if you take the predicted proteome of the virus, there is already 3 proteins that are predicted to interact with the virus. That's nothing to do with ACE2 that you see here, that are actually independently causing a cytokine release syndrome, and downstream could actually very easily start a cytokine storm without involving the normal cytokines like IL-6 that are at the bottom of this. So what we really believe is that there are multiple ways in which the virus can induce this aberrant immune system, and if we stop the immune system from going into a cytokine storm, we might also slow down the immune system that is doing its good job to slow down the viral replication. So it's a complicated decision for physicians how to treat patients, even now that we understand the disease much better. So here's the disease model that we came up with in a simple way. the virus infects, usually of course we know it uses ACE2, that disturbs the ROS system and we get the cytokine storm, but that's as such not so bad, the release syndrome and the cytokine storm, except when you have comorbidities and you have a lot of ACE2 and you're older, then with lots of intermediate actors like 47 genes and cytokines down the stream here, you can go to leakage or thrombosis or both. And both is of course pretty dangerous. So most people only get this first phase, they recover. Some people come to the hospital, if they're treated well, they recover. But some go this red arrow in the center and they may end up dying from all kinds of thrombotic and vascular problems that actually then kills them. And here you see a lung that is completely afunctional, as even a lay person could see. Fully filled with liquid, and even we think that based on this that ventilation is probably not at all always the most logical way to treat these people. So the idea now of the system is that I put this here in a petri dish to sort of emphasize that you can make a disease model like this, and we now have a better one, but you know, this slide is changing every day for the better, because physicians are giving us feedback, say put this to left, to the right. And here, to avoid that we promote one drug or anything, I just took all the drugs that are being mentioned in Wikipedia and Wikidata as being considered or tested on COVID-19. So you see the whole umbrella at the top is all the drugs, and you can see hydroxychloroquine there with very little connection to the model. You see even the BCG vaccine, which could actually cause a cytokine storm. So you see that a lot of drugs have very strong connections with a number of genes and cytokines in this model. That doesn't mean they should work, but at least they have a reasonable impact on this part of the biology that underlies the viral replication and the disease. And I think that we call this rationalization, so you can at least say, okay, I now understand why my drug may intervene in this system. And here you see, for example, aspirin, that is now known all over the world to have quite some impact in some phases of the disease. And as you can already see here, the bundle of connections to in the literature and databases to a lot of these genes, which are way beyond normal genes of the immune system only. There are the known ones like KNG, bradykinin, you know, and here you see the ACE ones, but there's others that we derived from the interactome with the virus. So there is a lot more to it than the simplistic way of looking at this model. And so you can put almost any drug virtually into this petri dish, do a rationalization and decide whether you want to take the next step to go to in vitro and later even clinical applications. So here you see a very nice example of Dino Prestone, which is in fact a synthetic form of prostaglandin E2, which is one of the things that goes up very strongly in severe patient sera. And you see in a more somewhat simpler model now, we filtered out a lot of not so relevant information, that this compound interacts with many genes that are central to the disease model. So it's pretty logical that it might work and do something good or bad, we don't know. So of course this model is far too complicated to look at for the whole picture. So here you see a subset of the model that we can easily filter and see, okay, Dino Prestone has a connection to all the genes that you see here, effectively the proteins, of course, that are in the disease model. So it's highly connected in this model. And if you look at the diseases it's already associated with in the literature, you can see that these diseases are also extremely logically connected. But which is interesting, that it is not involved as such in any cytokine storm annotations. Of course it's involved via the genes, but there is very few literature that says that prostaglandin E2 is really involved in the cytokine storm, which fits in the model later on. So what we do in Leiden, that's just an example, and then we go to the end already. We see that we have big data and AI algorithms or machine learning, and we have patients, so real world observations on the one hand, and on the other hand we have a big metabolomics center headed by Thomas Hankemeyer, a colleague of mine. We have all kinds of omics research, and we actually have organ on a chip where we can perfuse capillaries of patient or of tissue, lung tissue or whatever, with sera from patients and from controls, of course. So we can also check whether things that come out of this in silico model may actually work in vitro first, and then whether they are rational to give to people. So if you, for example, take the serum of a patient and you measure the metabolic profile of that serum, then you feed it and you perfuse it through microvessels in organ on a chip, we see that we can induce vascular leakage, and that you see that some measured metabolites and compounds, including prostaglandin E2, actually are much higher. So the endothelial cells, or that's what we expect, in the micro vessels actually produce, based on precursors in the serum that was fed to it, more of the same cytokine, and inducing this problem with the veins. So now that you have all kinds of information about people, you have the digital twin of a person basically saying what's the genetic profile, what's the behavior, what did we know about this person, what do we measure in the serum when the person comes into the hospital. We have the experimental twin to check very quickly an organ on a chip, which are organoids, and in vitro models we can also knock out genes and see what happens. And then we have a very rapid rationalization of what to potentially do with that patient. And what we are doing right now at the moment, and then I go to the end of the talk so that we have plenty of time for discussion, I hope. There is now 77 key cytokines and other compounds that we measure on every patient coming into the hospital. That will soon be more, but 77. And if we take the whole wide interactome of, for example, vasculitis that starts relatively early in the disease development, we see that 67 out of 77 genes in the center of this picture on the left-hand side are connected to both. So we now go for every column in the disease model that you saw before, and we try to see what are the most important biomarkers for that particular phase of the disease. When do we detect that the person moves in the direction of vascular leakage or thrombosis, which will then precede, lung, heart or brain problems later on. And then we hope to be able to soon rationalize our drug interventions with simple heparin or a monoclonal like tocilizumab against IL-6 or any other intervention at the right time for the right patient when it's in the right phase of the disease. Coming back to this disease model, for each of these columns you probably have a very different way of treating the patient. Now, finally, why don't we have this yet? Why were we taken completely by surprise, and why took it so long to get this picture? I dare to say here that if this picture would have been there at the beginning of the crisis and the outbreak of this new virus, the picture I just showed, that is now being seen by many other people around the world, could have emerged like months earlier. And I'm not even wanting to think about how many lives that could have saved. So if any time in history we need fair data now, because as you see here, it costs lives, that we cannot share the data. And now, of course, COVID-19 is also highly politicized. So now it's almost unthinkable that people send their data even to WHO or whatever. So the only way to deal with crises like this is distributed learning over fair data. And this is not only true for a crisis like COVID-19, this would be wonderful for material science that we discuss a lot in this meeting, and for many other ways. Even the Dutch bank says if we want to detect a pattern, for example money laundering, We need to go to different banks. They won't send personal data to us. We need to go there, run the algorithms, and take the results. So that's the future in my mind of modern open science research. So, my final plea, also for the rest of the discussion, whatever you do, please go fair. Thank you very much.